The good news there is we do have the new database level pricing offering starting at a minimum of 400 RUs. So, that's a little bit nicer, a little bit more affordable. It is a premium product in a certain sense. And I'll tell you why it's worth your dollars. Anyways, a quick introduction about me. You guys are seeing a random thing there. I'm just going to close that. There we go. That's better. So yeah, I'm Chris Anderson. I am one of the dev leads on the Cosmos DB SDK team. You can follow me at Twitter at CrandyCodes. You'll see me tweeting about random Cosmos stuff, serverless stuff, JavaScript stuff. If you don't like JavaScript, you'll probably end up having troubles following me. What things that I've done, I've basically worked on various PaaS products through my whole career at Microsoft for the last 5.5 years or so. I started on SQL DB. Then I moved on to mobile services and then web jobs. And web jobs are where I had a lot of fun because I got to take web jobs and turn that into Azure Functions. And I was the first PM on the Functions team. And then somewhere along the lines, I got tired of just like designing logos and doing marketing things and things along those lines. And I switched over to being a dev on the Functions team where I did the runtime stuff. So if you're using any of the Python or Java functionality on Functions, that was my last contribution there. And then recently I switched over to the Cosmos DB team to work on developer experiences, redoing all the SDKs. So if you've used the Cosmos DB SDKs in the past, that's not my fault. Don't blame me for that. The new ones, those are my fault. You can blame me for those. Since I switched roles, part of that process was a kind of finding myself thing. And what I've really found is that I like principles. I'm a principled person. And so I want to share some of my principles with you, and it helps you kind of to see some of what I'm going to talk about later on in my presentation. Black and white, everything is this simple, right? Just binary. But in reality, it's actually not the case. Everything is actually on a giant spectrum. This is definitely the case with, for instance, the word serverless. We always kind of hear about, that's serverless or that's not serverless, but everything is a little bit more serverless or a little bit less serverless. There's always kind of a line there. Same thing for all the various levels of, PaaS computing and IaaS computing. And then same thing is going to happen when you start using databases. There's going to be, you can assume more control and you lose responsibility here, and there's kind of a spectrum. But at the same time, I respect the fact that sometimes black and white is just easier to understand. And so we'll always acknowledge the fact that everything's on a spectrum, but we can lie to ourselves just to make it a little bit easier to understand. The other thing is that we're all running on stacks, lamp stack, mean stack, whatever you want to call your various stacks. And they've got various layers of things. And what you really want to do to grok your stack is to understand n-1. So we always endeavor to try to understand n-1 even if we're not using n-1. We don't want to have to manage n-1. So we want to understand, for instance, using serverless because that was the theme and it's in my head. We want to understand how the infrastructure is working to a certain extent, but I don't want to actually have to manage it. But it's nice to understand how it's going to work so that way when things do go wrong, I'm not entirely lost. And then the other thing, which I should have taken this advice as I was writing this presentation because you'll find a lot of weird random things, is oftentimes it's better to just do less. I think, once again, I'll call out to Alex's presentation. The world's moving very, very quickly, and it gets quicker every day. And the less you can do to achieve your goal, the faster you'll go. And so we want to endeavor to try to take advantage of as many things as possible that will help us move quickly without, ending up in higher costs. There's definitely a balance there, but when in doubt, do the simplest thing. So with that in mind, let's talk about actually Azure Cosmos DB and not me and my principles. But just to kind of make it a little bit more lighthearted, let's actually go and jump into a joke. What does Cosmos DB and the richest people in the world have in common? Any guesses? Programming models. Okay, I'm sorry. So Cosmos DB is a multi-model database. What the hell does that mean? What it means is that you can talk to it using our SQL API, which is not the best name for that API. You can use the MongoDB compatible API with the open source license MongoDB, not the new special license MongoDB. We also support the table storage SDK. And so if you are using table storage using storage today and you want something which has a little bit more oomph, you can go ahead and just swap over to the Cosmos version of the table storage SDK. and you end up getting just kind of Cosmos level throughput as opposed to storage level throughput. We've got the Gremlin API if you're doing graph. That's one of those hot things to do. Go talk to Brady about how much he loves that. And then the latest and greatest thing ends up being Cassandra support. So we've got Cassandra also built on top of that. And what that actually means is we don't actually have like Cassandra running or MongoDB running in the back end. We've actually taken those APIs, those wire formats, and we've modeled them on top of our underlying Atom record sequence storage layer. Basically, all these different database types can be modeled via ARS. And so what we've done underneath the covers is built an abstract storage layer and then built these interfaces which talks to that storage layer. And that allows us to go through there and get a lot of bang for our buck when we build these hard to solve, global distribution of data kind of syncing problems. We solve those in our own special ways. We can then go through there and then build things on top of that. So that allows us to build other databases on top of our core underlying database in a way which doesn't involve us having to maintain 5 different services. It's one service with 5 different APIs. Really, when I say ARS, by the way, the simple way of thinking about it is actually just the SQL API. The SQL API is more or less a direct kind of exposure of what our underlying APIs are. There's a little bit of stuff that we keep that's internal secret sauce because that's mostly not useful to customers. But when you're using the SQL API, you're getting the full feature set of Cosmos, whereas all the other APIs are going to be some subset of the superset of features that Cosmos has. So it's always worth thinking about if you don't know which one to choose because you're not familiar with one. I'm biased because I own the SDK for the SQL API, so you can take that in mind. But the SQL API has all the horsepower you need to solve a lot of your problems. But the nice thing is, like Cassandra, obviously has just a great ecosystem for doing big data workloads, doing Spark and things like that. There's just so many great things. There's no reason not to take advantage of that ecosystem at the same time. So you can definitely be very successful with Cassandra if you know Cassandra. So now that we've kind of thrown the multi-model piece out of there, like for the rest of this presentation, I'm mostly just going to talk about SQL because SQL is basically a superset of the functionality and everything else can kind of fit within that. So we're going to be mostly talking about SQL during this presentation. I want to kind of go through the other big pieces we have here. So turnkey global distribution, you can literally just add a new region and you'll get a new region up very quickly by just hitting a button in the portal or running your ARM template or whatnot. There's no new deployments. You don't need to go through there and deploy 2 different resource groups and hook them together or anything like that. It's just a button press and you're in those regions. The SDKs can either automatically start to talk to those regions and fall back over to them, or you can go through there and define which regions your SDKs talk to. How you configure regions depends on which model you're working with, because not all of the APIs we have directly supports kind of failing over within the client. So sometimes you have to do some work where you actually attempt to try a client and then you pass a region-specific endpoint into it. That's, for instance, the case with Mongo. If you want to use 2 different regions with Mongo, you've got to basically say which regions you want to use. But when you're using the SQL API, we'll actually go through there and kind of auto-figure which one we want to talk to based off of availability and some kind of ordered list. I'll go ahead and just combine the latency and the SLA stuff together because it's really a lot of the same conversations. The great thing about Cosmos DB and why you'd want to use it over something like storage, for instance, just generally ends up being the latency and the throughput you're going to achieve through it. For reads, your average read is going to be under 2 milliseconds. In the 99th percentile, it's under 10. And we actually have inside of the Cosmos DB dashboard metrics page, you can actually kind of see what for your region that level is. And every time I check it, it's always around, for the 99th percentile, or 6, but we promise definitely under 10. So it's really, really quite fast to do reads and also quite fast to do writes. Things like Cassandra can actually go through there and goes a little bit faster. We do some shortcuts when we're using the Cassandra API, so Cassandra can even do a little bit faster for those things. We also have some really nice SLAs that come along with those things. So we guarantee SLAs for high availability. I believe it's 5 nines and then a 5. And then performance latency, same kind of thing. We guarantee those latency numbers. We guarantee the throughput numbers that you see. And then we also have a guarantee for how consistent your data is. So basically, within our various kind of logic for how we achieve quorum on the various flavors of consistency, which I'm about to explain, we guarantee an SLA for how those things work. So all that is to say is when things go wrong, you complain to us and you get a refund, which is kind of nice. So let's talk about consistency models just real quick, and then we can ignore it, which is really nice. Another fun joke. So my name's Chris Anderson. Who here has watched The Matrix? Pretty much everyone, I'm guessing, for this crowd. So people used to call me Mr. Anderson, thinking that was like real fun to do all the time. It didn't get old at all. But it's relatively useful for this particular joke, at least. Consistency, oftentimes when you're looking at various document databases and things like that, it's kind of treated as either you've got very strong consistency and now you've got high latency because you're waiting on making sure everything is sunk all together, or you're entirely weak and you got to write your application to kind of just be durable to various consistency issues and things along those lines. And once you actually go through there, and anyone who's a fan of like academic papers on consistency in databases, you generally look at this graph. Like this is kind of the one that a lot of different papers reference, and it's a lot of different things, a lot of different choices. Well, the nice thing is that we've actually got levels inside of Cosmos, which makes your life really easy. And we've got all kinds of data about what the right ones are, and if you need to go through there and get something specific, there's a lot of different choices there for you to have. But in the end, what most people are going to end up using is session. It's a nice middle ground where you don't need to go through there and get the high latency that's involved with strong and bounded staleness. Those things are going to cost you, basically, it'll half your throughput compared to the other ones. If you go with eventual, you've now got the same problem of having to figure out your consistency issues. Session's really nice because within the same client, we basically, or anyone that shares that same session token, which you can actually pass around between requests, will guarantee that it's consistent for that given token. And that token basically goes through there and it knows which pieces it needs to actually be consistent and which ones it doesn't. And there's a lot of nice tricks there, and you can go look through our SDK code to figure out how that works if you want to. So yeah, just when in doubt, just use session. That's the nice, simple answer. If you don't need to think about it, then just use session. If session for some reason doesn't work for you, you'll run into it, and then you can explore the other modes. All right, so this is actually where the fun part comes for why you would use Cosmos versus just running, say, your own database cluster inside of Kubernetes. You can totally do that. Lots of people are successful at doing that, but there's a lot of hard problems to solve. So this is where the fun would begin if you were trying to figure out how to run that kind of thing in production. I'm going to go through there and dive through quite a bit of how we work underneath the covers, so you can go ahead and understand the N-1 piece. So basically, Cosmos is deployed into all 40 plus Azure regions. We're one of the first services that always has to light up in a region because lots of the other services take dependency on us for how they run. That's all split up into data centers and stamps and fault domains, and then we use Service Fabric underneath the covers, and everything's kind of deployed inside the Service Fabric. We break that up into lots of different processes, et cetera. On a single machine, we might be having multiple tenants. That's another reason why using a PaaS database is really nice, is when you're running your own databases, you've got to have enough spare machines for availability issues. When we're running in a multi-tenant service, we can go ahead and kind of share the cost of those things. So it actually costs you less when you go through there and try to compare the number of machines you'd have to provision yourself versus how many machines we have to provision. We can actually go through there and share some of that load. So the physical design there, mostly you would ignore because you'd just be running on VMs and deploying like Cassandra onto your cluster and things like that. Then it takes into account some of the logical design. You can kind of see there that tables, collections, graphs, they all map onto that logical containers concept. If you're used to using the document DB SDKs, they used to be called collections, but there was a lot of confusion between MongoDB collections and document DB collections. So as part of renaming ourselves to Cosmos DB, we've also renamed collections to containers. So just in case there's any confusion there. So all that stuff is kind of mapped onto a bunch of underlying stuff that basically just kind of picks and chooses which machines you're going to be talking to. When you end up talking to Cosmos from the SDK, we'll actually talk to directly when you're using direct mode to the underlying replicas themselves. And that goes ahead and has a lot of fancy logic for choosing which one to choose, which is most available at the time. And we'll kind of swap that as we're doing things like scale-out operations or split operations. When I say split operations, what I'm talking about is underneath the covers, we've got all your data kind of partitioned into a bunch of little tiny, I kind of think of it as like a mini database. Your giant collection is actually split into a whole bunch of partitions of data. And we have those across lots of different machines. What you want to do there is when one of those little ones get full, we go ahead and split it in half, and now you're automatically sharded onto 2 different machines. This is a really awesome feature. Anyone who's having to go through there and like reshard a database, that's a miserable operation. Figuring how to do it online is really, really hard. Doing it offline sucks because now you're offline and you've got consistency issues, et cetera. Cosmos will automatically go through there and handle that resharding of data for you automatically based off of the partition key that you set. And this is honestly the magic sauce. This is the #1 reason to use Cosmos from my personal point of view, just because it just takes away this huge database operational thing that you had to go do, and it just magically works. It magically continues to scale out horizontally. And then the last thing you've got to understand in terms of all that kind of stuff is it's all resource governed because it's multi-tenant. So we kind of break up each request into individual chunks called RUs. A read is a single RU. Inserts and upserts are going to cost more RUs. Deletes cost a little bit less, but still more. And queries take up even more because it's both a read and it has a whole bunch of index lookups and query complexity and instruction cost. So the queries are a little bit more expensive, and I'll break that down a little bit further. Okay, everyone's still following me. Because definitely as I was going through the slides, I was like, man, I really want to cover all that kind of stuff, but you're not going to follow me. But basically, what I want you to do there is know two things coming out of that. Is one, you don't have to think about any of that stuff anymore. Once you've seen it once, just understand that it's there. And then you got to answer these two questions as you're approaching Cosmos DB. How do you partition your data? Because that's obviously a key concept there. In order to achieve horizontal scale, you've got to go through there and choose the right partition key. And then how do you access your data? When it comes to accessing your data, you've got lots of different choices in terms of doing reads or queries or read feeds or change feeds, and there's lots of different options, and each one have cost impacts, and a lot of those impacts have a lot to do with how big your data is and what kind of data you're trying to access. So we'll walk through some of those cases here. Infinity is a lie, right? So I've been talking about how to scale Cosmos DB, and you can scale infinitely, but I mean, time is relative. There's a finite amount of energy and mass in the universe. The universe itself is just a giant disk riding on a turtle's back, so there's only so much space there. And then I get into further conspiracy theories. I'm pretty sure this is actually just a simulation for cryptocurrency in some higher level dimension, and this is all just for that sake. But really, infinity is a lie, right? So how do we actually break down what pieces we're going through there to try to achieve infinity? So a given item inside of Cosmos is at most 2 megabytes, right? So immediately infinity got really, really small right there because every single thing you store into Cosmos has to get broken down into a chunk which is at most 2 megabytes. And ideally, as we'll find out, probably a lot smaller. That's where you're going to get your optimal performance. And then a given partition key can have at most 10 gigabytes in it. Technically, you can go higher than that, but you have to call us, and we're like, tisk, tisk, tisk. Don't make us go any higher than that. So really, you want to go through there and figure out, you've got these kind of two horizons. You've got to make sure that you never go over 2 megabytes per document. And then for a given partition key, you never want to go over 10 gigabytes. And ideally, you never even really approach it for quite a number of reasons. And then you can have an infinite number of partitions, but infinity is a lie, but it sounds a lot nicer than you can have a lot of partitions. It sounds more impressive. So what's in a read? Sorry, this is another joke. Would a read by any other name cost as much? The answer is, borrowing from Alex here again, it depends. So pulling up this slide again, cost for Cosmos is you provision a certain number of RUs. You generally provision RUs in 100 RU increment chunks with a minimum number of RUs being 400. You can have RUs at the container level, or you can have RUs at the database level. It's not really worth going too deep into that stuff. It's just kind of worth reading the docs for those things. It depends on your kind of scenario for which one you want to choose. But the real thing to kind of think in there is, okay, well, query looks like it's going to cost me a lot more than read. So is it actually ever more efficient to use query than read? That's an interesting question to explore. There's a couple different ways of doing those reads, right? So I can read one item by ID and partition key. And this is generally going to be quite fast because there's no scans happening there. There's no searches. I'm just going to be a point lookup, and it's always just immediately I know where that data is, right? And so this should always be the fastest, right? That's what we'd assume. Well, we'll see. Read feed, well, this is probably going to always be very expensive because what I'm going to do is I'm going to read all the items, and I'm going to go, and I can actually say just a partition key, which you generally want to always specify the partition key because if you do a read feed for, a terabyte of data, you're going to read all that data. So partition key, you want to read just one segment of that data, and then a given partition key is going to have at most 10 gigabytes of data. Query feed allows you to go through there and specify a SQL filter. This is where I want to broach the awkward naming of the SQL API, because this is actually the only method that takes in a SQL query, and all the other methods within the SDK has nothing to do with SQL. So normally within SQL Server, you're going to go through there and do all of your reads via select star where ID is equal to whatever. You're going to do your inserts with SQL. You're going to do your deletes with SQL. You're going to do your table drops with SQL. This is the only command inside of Cosmos that uses SQL, and it only supports select. So this is the only place where SQL leaks through in the API. So SQL is an interesting name for the API, but legacy is legacy. And in this case, I can go through there and filter what's coming down there. So I've got a quick sample of here where color is equal to blue. I only get the blue squares in this case. And change speed is actually really fun, and I'll show a couple of really good demos at the end of this, where you can actually go through there and read every single version of every single item inside of your container. And so this is really, really useful for not only going through there and seeing what things were inserted and the order, because there's ordering guarantees in terms of what order we saw them actually getting inserted into the database. But then you can see each version as well. And each document you see is the full version of the document. So you'll actually see not just the changes, but you'll actually see the original copy of the document. You can build all kinds of really interesting things like with this. I'll show you just two examples of two interesting things with it at the end. But change feed itself is kind of an extra flair on top of read feed. But even here, you're going to have RU costs where every single document you read is going to cost you RUs. Change feed doesn't have the extra overhead that query feed does, it's worth noting. Query feed is the only one that has the extra index overhead, et cetera. Read feed and change feed are just going to charge you for the amount of data that's shoved across the wire. So worth considering those things. So let's go into the scenarios to kind of look at that. Let's go ahead and compare query and read. So in the case of doing just reading one document by its ID and partition key, if I do just a read on 1 kilobyte document, it's going to cost me 1 RU, because that's the definition of an RU, is a read on a 1 kilobyte document. If I query that one document using select star where ID is equal to 1, 2, 3, it's going to be 1 kilobyte document plus some constant overhead of doing a query in the first place. So in that case, reading the document is actually more optimal. Let's go ahead and scale it out, and I want to do 2,000 reads of that same document. Well, if I do 2,000 reads, it's going to cost me 2,000 RUs. And if I do 2,000 queries, it's going to cost me 2,000 RUs plus that query overhead. So in that case, the difference between those two are going to be much smaller, because that is, especially if I'm just, to be fair, that'll be C times 2,000 if I'm running 2,000 queries. But it's just not that big of a difference between the two of them. But where it's interesting is in that 2 megabyte document, doing that read, if I read the whole document at once, it's going to cost me 2,000 RUs to read that one document. But if I query one property off that document, which is only 1 kilobyte in size, that query now costs me only 1 kilobyte plus the constant query overhead. So in the case where I have very, very large documents, query can actually come through there and make it significantly cheaper to read documents out of my database. So it's just worth considering some tweaks there. Read in general is going to be faster for smaller document sizes. Query, once you go above a certain size, ends up being cheaper. And so that's just a way of getting more bang for your buck from RUs. So it's just really worth noting that you get 2,000 RUs versus 1 plus some constant RUs. And when you go through there, and the logical thing to go do there is write a console app that goes through there and compares them as you increment your data, document size, what the cost differences are. To save you some time, it's roughly about 10 kilobytes you cross that mark. So once you cross 10 kilobyte size for your documents, if you're trying to read just one property off that document that's relatively small, it's faster to query. As soon as you try to read more properties off the document, and the difference between those two things is smaller, then this line here is going to move up. And thus you'll slide along this line, and this number will also change. So it's worth always kind of running that simulation for yourself to optimize, should I be doing a read or a query based off of what I'm trying to get out of the database. But certainly, if you're trying to read 2 megabyte documents out and having each read cost 2,000 RUs, that's very expensive, and you don't really want to pay for that. So try to keep your documents small, and when you do have large documents, try to query for only what you need out of them. Sorry for any French speakers here. I'm butchering your language a little bit, but I wanted to have a fun joke again. Party pre, I'm probably saying that wrong, is effectively this notion that you want to have good design in architecture, which is, I'm butchering that definition as well, but it's basically all about trying to have good design. And it's also a good pun because I want to put the party in partitioning strategy. Choosing which partition key you use is a big part of what your database ends up doing, right? If you choose the wrong partition key at the very beginning and you insert a bunch of data, and then you figure out that's not going to scale right, you're kind of hosed. You've got to go through there and basically port your data into a new collection and do your partitioning that way, because you cannot choose a new partition key after you've created it on a given container. So what are the challenges you'll commonly face when choosing the right key? Well, you want your hot path queries, if you are going to have any SQL queries, to not go cross-partition. As soon as your queries go cross partition, your latencies are going to go up quite a bit, especially if you're going through there and doing a massive kind of cross partition query. You can do some interesting cross partition queries where you specify a fixed list of partition keys. So if you wanted to go through there and look in partition key A and partition key B and do that in a query, that one can actually work depending on the query. But if you just want to do a select star across all your partitions at a pretty quickly, once your data goes beyond a certain size, you're going to be hosed in your hot path. So make sure that you don't have a many partition query going on in your hot path. Your partition is ideally a fixed sized or has a logical cap well below 10 GB. If your partition can theoretically grow to O of n size and n eventually goes beyond 10 gigabytes, then you are going to run into issues and you're going to have to go think through how you're going to go and solve that type of design. It's not always possible to avoid this. For instance, if you have like a history log of something, well, history log, if you want to be able to go and query it, it's probably all going to be in one container, but eventually it's going to go beyond a certain size. So what do we do once we start getting close to 10 GB? There's a couple of options we have for us. You want to avoid splitting the data across too many partitions, because if you go through there and take a single document to kind of break up the size of things and split it into two different documents, well, every time you do a read of one document and you want to see a property for its child document, you then have to perform another read to go grab the child. And that adds latency because now you're going to make two network hops. And so splitting documents in too many different parts will hurt your overall latency unless you're doing client-side caching of things that can help you avoid having to do all the extra hops. And then finally, RUs per partition will be a fraction of the total amount. So you want to avoid one very hot partition key. What I mean by this is if you provision yourself 40,000 RUs, you're not going to get 40,000 RUs for a single partition key. You're going to get some fraction of 40,000 RUs divided by, at the very worst case, the number of partition keys that you have. But in general, it'll be much higher than that because we'll actually go through there and do load balancing across those partitions. And in the case that you have one very, very busy partition, we actually end up taking other partitions and splitting them off onto other things to make it a little bit less noisy. So underneath the covers, we try to do good things for you to optimize noisy neighbor issues and stuff like that for you. It's not perfect, but it actually ends up being pretty effective in most cases. So let's go through some strategies, some scenarios to kind of see the impact that certain partition key choices we'd make could have on us. So we could go through there and go with a very kind of poor man's solution of, I'm just going to go through there and have an incrementing number. And every time a partition fills up, I'm going to increment that number and then keep on inserting data until that partition fills up. Well, the good news is I've got a fixed partition size because I'm going to only ever go up to 10 GB and then move on to the next number. And it kind of avoids splitting data because I can store big documents inside of there, and so I only have the one document. But the problem ends up being that I don't avoid cross-partition queries at that point because as soon as I have a couple of those things, I'm going to be doing cross-partition all the time. And you can't avoid hotspots. You're going to have a lot of stuff stored all in one partition key, and so we can't split that data up into other machines and split a partition key out to its own isolated machine. It's going to have a lot of data in one partition key. So ideally, we wouldn't have 10 GB of data that we don't know how popular it's going to be all inside of one partition key. That way it can't get moved. Let's think of something that is kind of the same idea, but actually a little bit better. And that would be just choosing a random GUID partition key for every single new document. In that case, partition key was meaningless, right? Just a randomly incrementing integer. It's not going to do any help for any business logic. So a random GUID is actually better. It's actually funny because Brady and I had this conversation a little bit earlier, and he was surprised that you can have, wouldn't it be bad to have a million partitions? And there's actually just no impact on you because those partitions are logical partitions. The service is what decides then how to take that logical partition set and map it onto underlying physical machines. And so you can have a million partition keys and we still might just have 5 physical partitions for you underneath the covers with replicas and stuff like that for them, of course, but 5 main primaries. And you're still totally fine. And the nice thing with that is if one of those documents becomes really, really hot, we'll move that one partition key into its own machine to consume as many RUs as it wants, and you don't have noisy neighbors. So this is actually really nice because I avoid hotspots. But the problem here is, once again, my partition key is meaningless, and if I want to go ahead and do any kind of querying, I've now got to do cross-partition and query everything because I have a meaningless partition key. So let's try to choose a partition key which is more meaningful and see if we can solve the cross-partition problem. So we go ahead and choose something that's pretty reasonable, and it's what most people would use if they were, going and trying to use things. And it's actually not that bad but there's some cliffs in here. If we use city or tenant or some other similar kind of population feature, right? Not a feature of an individual in the population, but a feature of a collection of individuals in a population. We can now avoid going cross-partition, assuming our queries stay within a given population set. So if I've got an application that helps people go through there and deliver mail within a city, they're never going to go and try to look across 2 cities theoretically. So I'm going to avoid cross-partition queries, or at worst, I'm querying across 2 cities, and so now I'm querying just A and B, and that's still roughly fine. Partition size isn't fixed though. If I go ahead and compare my hometown and boondocks of Indiana, there's all of 1,000 people in that city. But where I live now in Seattle, there's, millions. And so that's not really a good distribution of data, and Seattle keeps on growing in size, and eventually we're probably gonna have more than 10 GB of data in that partition. So it's not really a good split. We do avoid splitting data because now I can store as big a documents as I want inside of there, but it also doesn't avoid hotspots. Once again, there's a lot more people in Seattle than there is inside of Danville, Indiana. So Seattle's gonna get really, really, really busy and potentially might start getting throttled, and we can't really split it up any more than it is, whereas Danville's gonna be sitting nice and pretty, and that's fine. So this can work to a certain extent. It's definitely better than choosing a random one, because your cross-partition query problem's now solved, and that performance ends up being really critical. But if in the end you think you're gonna go above that limit, and it's really up to the application, sometimes you can kind of live with, I know I'm not really gonna get to 10 GB. It really depends on the scale of your application. This can be a bit useful. But what's actually just a little bit better is to use, you can kind of tweak that a little bit, and you're kind of introducing a paging concept. You still can't necessarily avoid hotspots, because depending on which feature you choose, you can still have a very popular thing. And in this case, it still grew to 10 GB. That's still a really big partition size. But you do kind of have a fixed partition size scheme instead of there. By combining that first strategy and the third strategy together, you can kind of have just Helsinki 1, Helsinki 2, Helsinki 3. That actually works pretty well in practice for a lot of different cases where you do have this issue. And if it's one of these cases where it's relatively rare for you to have a partition key that needs to have multiple pages, this can work really well, because then those rare cases are the only ones hitting this, and everyone else that are in smaller towns mostly won't be hit by this problem. So this is one of those things that can kind of save you from that one kind of fixed size limit, even though it doesn't solve the hotspot problem entirely. So let's go through there and try one more tweak to a strategy, which is to kind of go down to something more scoped. And in this case, now instead of choosing a feature of a population, we'll choose a feature of an individual within that population, like user ID, as being a relatively good one to choose. If I choose this, then I can mostly avoid cross-partition as long as I'm only trying to query for a given user about that user. But as soon as I want to query multiple users at once, I am now going to go cross-partition, so I might need to solve that problem. And it really depends on what kind of data I'm storing about that user. If I'm storing an audit log of all that user's activities, well, eventually that audit log is probably going to go beyond 10 GB. So what am I going to do if I hit that case? But if it's something like user settings or user data, that one's probably going to stay below 10 GB depending on the case. Like if it's just like profile data, for instance. But I do avoid splitting data in this case, and I do avoid hitting hotspots, except for if I have like a very popular person. This is actually a case for a lot of social media sites. They end up having a lot of this kind of a partitioning happening. But what you end up doing is you have some weird issues, like where you've got unpopular people like me on Twitter, and then you've got Taylor Swift, who's incredibly popular. And the differences in their popularity means that you end up having hotspots for Taylor Swift, whereas this strategy works great for people like me. And what they end up doing is they end up just kind of going with 2 different data models. They take the Taylor Swifts of the world and they put them in something which scales differently. And it's an entirely different system, but it's one that doesn't scale horizontally very well, but you only have a fixed number of Taylor Swifts in the world, really. And then for all the Joe Schmoes, they put them into something where they just use the user identity feature. And so they kind of mix and combine these strategies. And that really ends up coming down to what you'll do is you'll find corner cases that might need exceptional solutions, but then you can solve the general case with a relatively easy strategy like this. So let's go through a couple of scenarios just to kind of see how that works, and then we can jump into something a little bit more interesting. So user ID is the partition key. The pros are going to be no cross-partition on the hot path, no data splitting required, mostly fixed size. But that con is going to be the Taylor Swift case. If Taylor Swift gets hit, you're going to get throttled, and then no one's going to be able to go ahead and see the latest album that came out. Then you've got chat room. It's another interesting idea. Cross-partition in the hot path, no problem there. Data splitting is not required. And the room might get rate limited, and that might be a problem that we want to solve eventually. But the nice thing here is at least there's no impact to other rooms because it's limited to just the room. So worst case is a given room is very popular. And we need to solve that with maybe some like local caching or something like that inside of the server that's serving the chat room information. But it won't affect others, which is really nice. But the size will eventually go over, I mean, that's a typo there, 1 GB, 10 GB, right? Because eventually your chat will go up over time. So you can mitigate that by doing things like backing up that history. If anyone's ever like scrolled through Teams or Slack, you go up a certain amount and you don't have that history local there anymore, and it's going to go and fetching it from something that's a little bit more cold, right? So you can do the same thing here. You can go ahead and store that into a cold historic partition, doing the paging solution as a way of trying to solve that problem, or taking that data and backing up into blob storage using the change feed, and then the data is stored in blob storage for when you go through there and grab chunks of history at a time. So you can go ahead and add those pieces in there to kind of move the data out of the partition when it's no longer useful anymore. Cool. So that was a whole lot of information all at once. And I want to kind of show some really cool samples for how you can go ahead and actually use Cosmos in practice. A lot of them end up using change feed, mostly because change feed ends up kind of having more reaction and fun to it for the samples. But I've got one thing that we wrote for build, and we've kind of used it quite a bit. It's got a lot of fun features to it. So effectively what this application is, and I'll break out and show it to you before I walk through the architecture. So what this is it's designed to be a real-time drawing canvas. So you want to go through there, and this is a 1,000 by 1,000 pixel image. And I want to be able to go through there and mark up the image in real time with people all around the world. That was the idea here. And what is happening here is every time that I'm drawing, what's actually happening is I'm inserting documents into Cosmos DB that records who actually inserted that pixel, when they inserted that pixel, what color they inserted that pixel with. And I can go ahead and do these long brush strokes, and so I can actually go through there, and I also have information about the stroke itself. So I know these pixels were drawn together, and these pixels were drawn separately, even if they cross paths. And so I'm storing all the information inside of Cosmos. The nice thing is that now I've got that long history. I can actually replay the whole thing, and I've got information about which user did what action going all the way back in history. What's happening is you're seeing you're seeing the pixels show up on the other screen here in pretty close to real time. Got to forgive some hotel internet latency. And what's happening there is it's actually going ahead and using a combination of change feed and SignalR. And we go ahead and have a little bit of cool tricks to help deal with the fact that SignalR is not durable, right, Brady? And so we don't want to go ahead and use SignalR for anything where we really care about those messages definitely getting delivered. If we had pixels getting dropped as we're drawing, and you might have seen that with some of when I was first drawing it, the internet was a little bit more shaky. You really want to make sure that you do eventually get all the pixels. And so there's a couple of different strategies we can use to solve that one as well. So looking at the architecture slide, and then I'll dive into some code. What we did is we went with a hot path for getting the changes to the browser. So that way you see the changes in the browser relatively low, with low latency. And that's where SignalR is great. SignalR is great for real-time kind of notifications of events. So what ended up happening is the client, the browser, which is just a static page, calls an API and a function app, which actually inserts the stroke. And we generally break the stroke up into pieces, so that way we don't have to wait for the whole stroke to finish. We actually receive portions of a stroke, and then we kind of put them together later on. Then, once it goes into Cosmos DB, we've actually got SignalR listening on the change feed from Cosmos DB, and that's what sends down the individual partial strokes down to any other client that's listening. And then it renders those partial strokes as it's getting them. Obviously, SignalR can potentially be lossy, and so what we also have happening is a function listening on that same change feed, and you can have multiple subscribers to a change feed. There's no real impact there. Basically, each one can keep its own cursor separately, and they can read change feed at different paces even. So what's happening there is that function is actually reading that same change stream and then storing the results into blob storage. And what it's doing is it's just storing the kind of rendered view. So rather than it having being just a blob of all the changes, it's just a blob of the actual picture as it is right now. And that means when new browsers start up, and actually join the client, it doesn't have to go through there and replay the whole history. It just goes and grabs the latest blob and then starts drawing on top of that blob. What we also do is that client pulls against that blob, and you can kind of configure how quick you want it to do it. I actually have it in there where if SignalR starts acting up, I have it pull more frequently, and if it's relatively healthy, it pulls at like 30 seconds. And that blob is behind a CDN in my production environment. For this demo, it's not behind a CDN because it doesn't need to. But you can use a CDN to kind of make sure that you're not having to hit that blob like 30,000 times a second. It's only getting hit once a second by the CDN, and then the CDN's hitting the cached one to all the clients. And so that's how I go ahead and I get both real time via SignalR, and then I have the kind of durability of blob storage to actually store the real current view of things, and then they catch up. And then I play some cool tricks in there, and if you go and look at the sample, you can kind of see an example of this. I want to make sure that if SignalR is behind, that I don't have the blob get pasted, and then I replay new drawings on there that had already got erased. And so I actually have a bunch of timestamps in there to make sure that I never render a SignalR update on top of a blob that's actually ahead of the SignalR change. Because that can happen too, is your SignalR real time stops being real time and it's actually behind the blob storage. And so you have to go through there and deal with some of those kind of latency issues. And I have a relatively cool algorithm inside of there for how to do that. So looking at some of the code itself, there's a couple of things that I think are interesting and worth pointing out. So I broke it up into a couple of different apps. I've got a notification, which is just an ASP.NET Core SignalR application. I've got my update processor, which is just a function which actually has the update processor. And it's got a couple of nice metadata things. I've got a canary in here, which makes sure that the thing's always listening and staying awake. But this is effectively going through there and just reading the stream, updating the blob, and then storing all that. I actually skip bindings for the most part in this case and just using one static client. It just made it so the code is a lot more reusable. So if I wanted to lift the same library, I've got this blob client thing out of here and put it inside of a web app instead. I could go ahead and do that swap and I wouldn't need to go through there and like rewrite everything so I wasn't using the bindings anymore. So that was just a choice. And then the other cool thing that's worth looking at is I had a lot of authentication logic I wanted to go do because we actually opened this up and it's still public at pxdraw.azure.com for build. So anyone could go through there and add pixels into it on it at any time, including when like Scott Gu is doing the demo. I didn't really want people going through there and freeform drawing rude images while Scott Gu is doing his demo, so I had to rate limit and be able to block people who are bad actors. And so I did all that logic inside of functions itself, and the cool thing with functions is it's got this feature inside of it called Easy Auth, but it's called authentication and authorization inside of the portal. And I can actually go through ahead and throw inside of their Azure AD in front of a web app with just web UI. So I didn't have to write any login logic inside of my function app itself. I let the Easy Auth feature go through there and put AAD in front of my function app for me. And I also put Twitter auth in front of it. And I let people go ahead and choose, do you want to log in via Twitter or AAD? Microsoft employees could log in with AAD and they got more permissions, so they could go through there and like erase things that were bad. And Twitter users were getting rate limited to doing 1 pixel every 5 seconds. And so they couldn't do anything too quickly that was too rude. And the trick there is you had to kind of do a lot of work in terms of the function's default cores ends up being relatively simple. It just kind of goes through there and says you're allowed origins, but if you want to modify your allowed headers and things like that, it doesn't work. And I wanted to go ahead and pass some JOT tokens around, basically. And so I actually go through there and apply my own cores rules, and I don't use the portal functions cores rules. And all that's doing is setting the cores headers, and it's handling the case where I'm getting the options verb coming in. And in the case of it's an options verb, I only send the cores response back to the browser. I've actually got a thing in here to actually get a user so I can tell whether the user's logged in and what permissions they have. And what permissions they have determines the canvas's behavior. The user could obviously hack that client and change the JavaScript to let them try to do a brushstroke. But the underlying API is still going to enforce the rate limiting. So if they tried to use the brushstroke feature, it would only insert 1 pixel, and then the rest of them would fail. And so that can kind of controls there where you kind of do a little mix of those two features. And then update pixel itself, all this is doing through there is making sure the user is actually logged in right. We go through here and we look to see whether or not they're logged in by grabbing the XMS client principal ID header off there. And let me just zoom in a little bit. So you can see I've got this MS client principal ID, and it actually has the identity provider as well. And that allows me to differentiate between Twitter and AAD users very quickly without having to go through there and like look up the user from Cosmos. Ideally for these hot path scenarios, you would look up as little information from Cosmos as possible because each lookup is going to be a latency call. And I wanted things to be pretty quick, especially as I had this scale out. And then it goes through there, and I go ahead and I break things up into services. Once again, I opted into kind of writing my own services underneath the covers. These are all singletons that run inside of here, so that way they're kind of long and stateful, and I knew how to do connection management with them, as opposed to using the bindings. And then I've just got a service for each of these things, so that way it was nice and reusable. So I've got this pixel service here that goes ahead, and it manages inserting batches, because when I'm doing brush strokes, I was calling them batches underneath the covers, and it handles going through there and updating them and making sure that all is successful. So yeah, and then the notifications is just SignalR, and effectively we just got the change feed reader, and it just sits there, and it's an ASP.NET service, hosted service, and we start our change feed, and every single time we get a batch, we then go through there, and at the end, pump it out onto SignalR. This one took some tuning. If you just go through there and have it send the whole brush stroke on SignalR, if you have a very large brush stroke, well, SignalR doesn't like large messages, it likes smaller messages. And so we actually had our own kind of debatching API where we wanted to make sure we did send batches, because that was faster to send more than one pixel across the wire at once. But if you wanted to send, a giant 4 megabyte brush stroke over the wire, it didn't like that. And so we went through there and we had our own batching where we took the brush stroke and broke it up into mini brush strokes again within the SignalR piece, just to send it at the right speed through the wire. And we have a lot of smoothing stuff that we have to do in there to make sure that it actually goes over the wire fast. And on the client has to then smooth it as well to make sure that it's not drawing things in big spurts. You want it to look like a human is drawing the thing, even if it's running slower. In that case, we're trying to optimize for human eyes. And so we actually went through there and did a lot of things to make it look like a human was drawing it, even if it was like a second slower than we actually received it in the client. Because we wanted to have enough information to kind of draw like a human would draw within that screen. But you also want it to be fast, so that way it's impressive in demos. So it's a lot of fine tuning to kind of reach that point where it looks good to the eyes, but also feels fast to the user. And so yeah, this is up on GitHub. I think I have the link in the bottom, but if not, you just look at my GitHub user ID. This is a really great example of using a lot of different kind of serverless features all together at once across Azure, and it's a kind of a great picture of trying to do like low latency data manipulation with Cosmos DB. It looks like I have time to do bonus demo. We had a feature come out, I think it's last month. We introduced the ability for you to set for Cosmos DB cores. One thing I didn't talk about is that Cosmos actually has two different protocols. It actually has a TCP protocol, which allows you to talk directly to the replicas underneath the covers. But it also has a gateway that speaks HTTP that will then go through there and proxy that call down to the replicas for you. On that gateway, we gave you the ability to go ahead and use cores. The trick with using the gateway mode is that it has a bit higher latency because there's the intermediate jump. But the pro is that you can now use things like HTTP for things like cores. You can talk to it from the browser. And for different IT groups that have like proxies required for kind of going outside of the boundary, you can use standard off-the-shelf HTTP proxies instead of having to write your own TCP proxy, which is a little bit more work. So there's some benefits to HTTP for certain cases. What this means, though, is that I can go ahead and very quickly now use the new JavaScript library that we've got published. That JavaScript library is now isomorphic. So you can take the same library and run it both inside of Node.js and run it inside of the browser. And it's written so it nicely works with Webpack and things like that, so that way it shrinks down to a very small bundle. We use the same SDK for the Data Explorer and the portal. So we're actually running our Node SDK inside of the browser, inside the portal, and that's what powers the Data Explorer itself. And so we can see a quick example of how that works here. So the way that you go ahead and set cores, got to refresh this. There's a new cores tab in the portal when you're using Cosmos DB. And you can set it to be either a list of domains, or you can set it to being star if you want to go ahead and just be lazy and allow everything. You shouldn't use star, but I did it for demo purposes because I'm lazy. But you should not. That's a bad idea. But I did. So you can judge me. And then the nice thing here is I can now go through here and type, hey, IglooConf. I add my item and cross my fingers that everything is still working. Let me refresh my pages. That's what happens. So now I can go through here and set this up here, and I'll do hey IglooConf again. And I add this, and it actually gets added to both places. And what's actually happening here is that same change feed feature that required me to have all that complicated SignalR stuff to get real-time changes to the browser, I can actually run the change feed from the browser now. So rather than having all that complicated pumping logic that I have to go ahead and do to pump stuff via a server from my Cosmos DB to the browser, I can just run the change feed from the browser itself, and boom, I get the changes there. What are the downsides of that? Well, if I've got, 10,000 subscribers using my web application, I've now got 10,000 people reading my change feed, and that can be a lot more expensive than having a SignalR server sitting there and doing the pumping for you. So there's some trade-offs to be had there, but if you're writing just like a simple business app, you can write this very, very quickly, and then if it needs to scale out to 10,000 concurrent users, go through there and optimize so you're doing less reads against your Cosmos DB. But the code here underneath the covers, it's literally just, I've got my to-do service here. It's literally just going ahead and bringing in a Cosmos client from Azure Cosmos itself. And I can go through here and I get my database and container reference, go through here and do everything. I've got my change feed right here, and I'm just pumping that. It's an async iterator inside of JavaScript. So I'm just pumping the async iterator, and every time I get a page, I go through there and I render it inside of that table there. So it's just that simple to use change feed in the browser, which is kind of nifty. Some tricks: don't put your master key in your browser. It's a bad idea. You got to use the resource token model. So you'll end up having like a function app or a web app sitting there somewhere, which will give you a resource token, which is a scoped set of things. It'll only do a read on a given user's partition key, for instance. And then you can go ahead and use the client from the browser in a safe, security way. So with that, I think I'm at the end. Yeah. So those are the content in there. I wanted to kind of go a little bit deeper to kind of give you guys insights deeper into Cosmos rather than just doing a hello world demo. But if you've still have questions, if you have questions about some of the other APIs like Gremlin and things like that and how that works, you can send an email to askcosmosdb@microsoft.com, and all the team is behind that. And we've got really hard to meet but fun SLAs about how quickly we respond to them that we've set ourselves. And so we try to respond to those things within a day. They actually create an ICM ticket, which is our underlying support ticket. So when you send an email to that, it creates a support ticket. It just isn't linked to your account. So that's how we track them. You can send an email to me if you have any kind of personal questions you wanted to ask and that you didn't feel is appropriate for a wider alias. Feel free to email me. And you can also go ahead. My DMs are open on Twitter. Feel free to ask me questions. And I guess I didn't put the GitHub links there, but you can find my GitHub for my Twitter profile, and you see all the samples I've written for Cosmos and functions over the years there. So with that, I only have 2 minutes if there's any questions, but otherwise we can give time to Dan. Yeah? Okay. Thank you, everyone.